So for the next several videos, I'd like to make a pivot to looking at the flow of electric charges in wires and other electric devices. So on our way to that, I want to spend some time defining electric current. And this can be done in analogy to what we've already done for fluids. If you remember when we took a look at fluids, we could define the rate at which, say, a river was flowing if, say, you drew a plane across the river and you counted how many liters of fluid went by every second. So when you did that, you came up with a quantity that was called the volumetric flow rate, which we also found was equal to the cross-sectional area of the river times the speed of the river, assuming an ideal incompressible fluid, all that good stuff. So it turns out that the analogy between fluid flow and flow of electric charge is actually pretty darn close. And there's a lot of stuff that we will be able to do in analogy to fluids. So we'll start by defining what we call the conventional electric current. Now, we usually don't bother saying the word conventional. Basically, it's one of those, we only say conventional if we're worried about other kinds of currents and we're really being careful to disambiguate. But normally, if we just say the electric current or even the current, we mean the conventional current. So let's work toward that definition. So it's the same kind of idea. Now, instead of standing by a river, we imagine that we're standing by a wire. And so in this drawing, either this is a really big wire or this is a really small person, but either way, go ahead and roll with it. Again, it'll be the same kind of idea. We imagine cutting a plane through our wire, like say maybe through here. And we just sit here and we count all the charges that go by in a second. But we do have to be a little careful about this because we've got the complication that we didn't have with water. I mean, water, if it was flowing one way, is just flowing one way. From the perspective of an electric circuit, it doesn't really matter if you have positive charges flowing to the right or negative charges flowing to the left. They would both do the same thing of attempting to make this side more positive and that side more negative. In fact, we'll even see in a future video when we look at batteries a little more carefully that it's even possible to have both kinds of charges, both positive and negative, moving in opposite directions at the same time. So what we do is we define the conventional current, and the usual symbol for that is a capital I. And it's just defined as the rate at which charge goes past some location every second. So we define the conventional current to be this time rate of charge. And so by convention, and thus it's called conventional current, this points along the direction of positive charge flow. It also means that it points against the direction. Oops, sorry about that. That should just say along. It points against the direction of negative charge flow. So in a lot of practical situations, the charge carriers will be electrons. So if, say, this were a copper wire here, then the actual charge carriers would be negatively charged electrons. And we would say that we have an electron current that points to the left, but we would still say that that is a conventional current pointing to the right. Remember how I said that when I went over Franklin's convention for defining positive and negative charges, that you were going to wish that he really made the other choice? This is that moment there. So yes, what's usually happening in electric circuits is if we say that we have a current flowing to the right, in other words, a conventional current flowing to the right, what's really going on is we have electrons going to the left. Now you might say, well, why don't we just redefine everything? Well, the thing is that not all electrical systems act that way. For instance, I've already mentioned that in a battery, we have both positive and negative charge carriers moving in opposite directions, but both contributing to the same conventional current flow. And also, especially in biological application, where you look at the flow of signals along nerves, that's usually positively charged potassium ions. So it's entirely possible for the charge carriers to be positive or negative. It'll just turn out that here, where a lot of times we're just considering the flow of electrons through wires, we would kind of wish it was the other way. But somebody's going to have to be grumpy one way or the other. So I'm perfectly fine with ion current and conventional current matching in a nerve, and just having to acknowledge that that means that electron current and conventional current point opposite each other in a wire. So anyway, the units of current here are going to be coulombs per second. And one of the sort of recurring themes that you're going to see as we work through this material is that in electricity and magnetism, virtually every time we multiply or divide some unit by something else, it picks up a new derived name. So in this case, the standard unit of current is the ampere. That's A-M-P-E accent grave R-E. Its symbol is just a capital A, and it's defined as being one coulomb per second. Now, with some other units, you'll notice that names got truncated. For instance, the volt is actually after Alessandro Volta. The A on his last name got dropped. And the farad is after Michael Faraday. The AY at the end of his name got dropped. For whatever reason, the official name is ampere. However, in English-speaking countries, this often gets just abbreviated to amp. And that's how I'll probably end up saying it most of the time anyway. And you certainly do not have to draw the accent mark if you're doing this in English. All right, so let me put out a little bit of a conundrum for you here. And this conundrum is if you throw a switch, say if you're turning on the lights in your room or something like that. In fact, let's just go with that example. We'll eventually work out that the electrons in the wire move at a whole walloping about 1/10 of a millimeter per second. Now, there's probably a few meters of wire between the light switch and the light bulb. So why is it that when you throw the light switch on, you see light right away, when the electrons that are over by the light switch are going to take probably a little over an hour to get to your light bulb? And yes, I know I'm thinking of this as DC. That's because we haven't gotten to AC yet. So pause and think about that for a second. All right, so it turns out that, yeah, the electron is going to take about an hour to move through the wire. However, what will go through the wire at very quick speed, the speed of light in the material, so for copper, that's about 10% or so of the speed of light in a vacuum. The electric field will propagate at the speed of light in the material. And so when you turn on the switch, you propagate an electric field through the wire, and then the electric field that has now been set up at the light bulb is what will make the charge go through the light bulb. Now at this point, I'm expecting you to jump all over me and say, but wait a minute, didn't I say before that the electric field inside a conductor is zero? Now I seem to be saying I'm not. So what's going on with that? All right, good. I'm glad that you caught the important caveat that before, when we said the electric field is zero inside a conductor, that is when the conductor is in equilibrium. We're going to see that here we are not in equilibrium. In fact, it's what's called a steady state condition. And that's what we're going to be looking at in the next video. So catch you over there.